Okay, so as you can see, something is already written at the blackboard behind me. Okay, so what is that? Partial differential equations, right? So from today onwards, I'm going to start partial differential equations. But as you can see, I have already spent around like 29 classes in ODE. So PDE, I am not left with that many classes. Okay. So what I'm going to do, I'm going to emphasize more on first order partial differential equations. So you may be under the impression that because I'm going to deal only with first order partial differential equations, I mean, this is much easier than second order and higher order. It is not like that. You will see that the way you learn partial differential equations simply by solving the general form of the second order linear partial differential equation, to be precise, linear or quasi-linear. Okay, in terms of your elliptic, hyperbolic, and parabolic equations, you will see that this is much harder. Okay, and I guess many of the concepts you didn't study in your MSc and BSc days. That is why this is going to be more important. Okay, and somehow it's sad also because I was really enjoying that ODE part. Okay, ODE part I haven't taught it to the PhD students before, so that is why I was enjoying it more. But the PDE I have already taught once. Okay, so now. Can you tell me what is a partial differential equation? Can anybody tell me? Don't go for some bookish definition. Just a general notion will do. What is a partial differential equation?
A differential equation which consists partial derivatives, and the differential equation depends on more independent variables.
Okay, fine. So basically, whatever you told the first part, that itself was good enough. You didn't have to tell about, something depending upon more than one independent variable. See, so a differential equation consisting of your partial derivatives, right? Partial derivatives. Partial derivatives. So partial derivatives means if you consider the partial derivative of a function say phi, it has to be a function of more than one variable, right? It has to be a function of more than one variable. Okay. So what I'm going to start, I'm going to start with the definition of a function of two variables, say function of two variables, and which can easily be extended to a function of n variables. Okay, but before that, let me tell you that the classification of partial differential equations into linear, non-linear, then homogeneous, non-homogeneous, quasi-linear, semi-linear, all this stuff you have already learned. Okay, and whenever I will come across them, like say whenever I have to tell you about them, I'm going to tell you, right? So what I have done, I have already uploaded today's class. So at the beginning of those slides, you will see all those definitions. Okay, so I'm not going to touch upon them. So I'm going to start from a function of two variables. Okay. So what is a function of two variables? So obviously you know that it has to be a function of two variables. So that is why what we are going to do, we are going to consider some domain D in R2, right? Okay. So that means this is a function of two variables from this D to the set of real numbers. It is nothing but a relation that defines a unique real number to every point. Say suppose this is my xy plane. This is my xy plane. Suppose this is my D. This is my D, right? To every point, say xy. xy, this f uniquely determines some point, say, which is denoted by f of xy in the real line. So this line in fact represents the real line. Is it okay? Fine. So again, I am going to show. I mean, you are going to have much beautiful picture than this. Okay, and then along with this, this graph of a function, it is very important. Graph of a function. Of course, since I have started with a function of two variables, we can function of two variables. So I am going to consider the graph of a function of two variables. Okay, so you know that the graph of a function of one variable, it was nothing but a what? Graph of a function of one.
Line.
It is a curve or line, say. Curve to be precise, right? And then the graph of a function of two variables, it is going to be a surface, right? So that surface you are going to consider in 3D space, right? Isn't it? The surface is going to be generated by a function, right? The surface is going to be generated by a function. So that means the surface is going to be the collection of some points in the, real space, right? So the graph of the function f, say, right? It is going to contain some point belonging to R3, right? In such a way that your xy, of course, here I have defined xy belongs to D and j equal to f of xy. So this is the definition of the graph of the function. If you want to write in some mathematical way, right? So let me just show you, much better figures. So here, this is so this I have already told you. A function f of two variables is a rule that assigns to each ordered pair of real numbers xy in a set D a unique real number denoted by f of xy. So the set D is the domain of f. This you already know, and its range is the set of values of f takes on, that is f of xy, such that x, y belongs to D. So this can be a pictorial representation of function of two variables. Okay. So and then if I go to the graph, so it is going to look like this. So graph, visually, it is going to represent a surface. It is going to represent a surface. And here, you can see that in this particular figure, the surface is lying above xy plane. It doesn't necessarily so, because for the visual pleasure, to be honest, it is drawn in that way. It is not necessary that it is always going to lie above xy plane. Okay, right? And then let us just introduce you to some of the surfaces. For example, some of the graph of the functions represented by surfaces. So, for example, here you can see that this is nothing but x squared plus 3y squared into e to the power x squared minus y squared. So you should always remember that whenever you have something like e to the power x squared plus y squared term involved, you are always going to have something like some bell-shaped surface that you should always expect. Okay, although the bell shape can be generated through some other function also, but generally this is going to generate a bell-shaped surface. Okay, so similarly, this is sin x plus sin y. This is sin x sin y by xy. So these are, pictures of different surfaces. Okay, so now let me come to the definition of vector field. So can anybody tell me what is a vector field? Say, suppose I want to consider a vector field in space, 3D. vector field in R3. So what is it going to look like? What is it going to look like? What is it going to look like? Yes? It is nothing but a collection of vectors, in 3D space. Okay, right? So what it is going to do at each point in R3, X, Y, J, I will be able to define something like this, right? Through the vector representation. So that means I should be able to define a vector at each point in R3 through the definition of some functions of 3 variables. So then it is going to represent a vector field in R3. And let me tell you that this vector, in order to represent this, I am going to use this symbol, v1, v2, v3. So if I use this symbol, then you should automatically, infer that v1, v2, v3 are nothing but the components of that particular vector along x, y, and z directions respectively. Of course, here I can jk, kk, they are unit vectors along x, y, and z direction. Okay, so like I can show you some of the pictures of vector field. Like this is what, let E be a subset of R3, a vector field on R3 is a function f that assigns to each point x, y, z in E. Here I was defining vector field in R3, but they are defining on a subset of R3, right? So what it does, it assigns a 3-dimensional vector f of x, y, z at each point x, y, z. So it is going to look something like this. Like say all these are, so this is a vector field in 2D. These are all 3D. These are all 3D vectors. So can you tell me this one? Like say the way it is drawn in this particular figure, you can see that all are moving only along direction parallel to z axis, right? So that means your x and y component of them are going to be 0. So you can see that in fact this vector field is simply defined by jk. Is it okay? Fine. So now let me come to space curves. Right? In fact, you already know space curve. Any idea what a space curve is? Space curve. Yes? Yes, can anybody tell me what is a space curve?
So this is one kind of generalization of the curves. Means curves.
That is
kind
of a bookish answer. Like, see, a space curve is nothing but a curve in space. Okay, fine. A space curve is nothing but a curve in space. But the way we are going to define it, it is going to be slightly different here. See, you have already got introduced to the concept of trajectory, right? Right? So trajectory, in fact, it was nothing but a space curve, isn't it? Trajectories, if you consider it in 3D. Although we were dealing mostly with 2D trajectories, but if you consider them in 3D, right? So they are going to represent some curve in space, okay? So now what we are going to do, say, suppose I consider an interval, I equal to say AB. I equal to AB, right? So then, if I define these functions x, y, and j, x, y, and j, x, y, and j, okay, from the interval I to the set of real numbers, all of them, all three of them, right? So then, what is going to happen? What is going to happen? Say, suppose I have certain x a equal to say something like x naught, x, sorry, y a equal to y naught, then j a equal to say j naught, right? And then, like, if I run all my points between A and B, right? So then, suppose this is nothing but the point x naught, y naught, j naught, right? So x naught, y naught, j naught corresponds to the value A in the interval, right? So then, if I run my t through this interval, then what is going to happen? It is going to generate a curve in space, right? So this curve, so that means if I define this curve in this interval, so definitely the end point here, end point if I call it xf, yf, jf, so then what must happen? What must happen? Your xf must be equal to your xb. This is similarly yb. This is similarly your jb, right? Okay. So this is the way we can define a space curve. Okay. But now, like say visually, I mean you are seeing a curve here. But what I want to do, I would like to associate the curve to be defined through a single vector. Like say I want to define it to be, like say earlier what was happening, if when I was defining a vector field, so then V was a function of x, y, z. I mean then it has component V1, again a function of x, y, z, and then V2, then V3, right? So now suppose I take any point here, say T, whose coordinates are x, y, z, right? And suppose this happens at a particular second, right? This happens at some, say, value of t. I'm calling it simply small t, say. Okay? Or if you consider a to be 0, say suppose t represents time, right? So then we start at t equal to 0, right? And at a particular instant, if I consider p to be the location, of a particle starting at x naught, y naught, z naught, right? So then what I'm going to do, I'm going to draw a vector from the origin to this point, and this vector I'm going to call as r, right? So as you know, what r, like if you draw a, if you draw a perpendicular from P to your xy plane, P to xy plane, and then if you take this, then what is going to happen? See, if the coordinates of P is x, y, z, so then basically what is going to happen? This length is going to be x, this length is going to be y. So that means your what is happening here? So basically, I can consider a vector xi along this. So that means what? This xi I can simply write like this, or simply what I can do here, along here, this is going to be yj, since these two vectors are parallel. So this vector is yj, right? So by summation of two vectors, this is the sum of xi plus yj. This one, right? This one is nothing but xi plus yj, right? So then sum of this plus this again, although I mean this k is along z axis, but I can take this unit vector along any parallel direction of z axis. So this factor is nothing but jk, right? So that means what I get, I am getting r simply as xi plus yj plus jk, right? But here you can see that r is a function of t, right? So this is simply xi ytj jt k. Okay, and of course here I am also assuming that x, y, z, they are not only continuous function with r, but I am also assuming that their first order partial, not partial, their first order derivatives with respect to t, they are also continuous on I. Okay. Again, why? I mean, I want the first order derivative also to be continuous inside I. There is a hidden agenda behind that. I'll unfold it in short version now. Okay. So now, so that means what we can do, a space curve can be represented by a vector like this. So if you know the range of t, then you can easily draw the curve, isn't it? Is it okay? How, I mean, a space curve can be defined through a vector. Now it is clear. Okay.
Yes, sir.
Fine. See, for example, suppose I am considering the curve represented by the vector, say cos t, sin t, say cos t, sin t, say. And okay, suppose it starts at t equal to 0. Suppose it starts at t equal to 0. Okay, so can you recognize it? Yes, can you recognize it?
Is it a helix?
Yes, it's a helix. Yes, it's a helix. See, if you want to draw it like initial point is cos 0, that is 1, 0, 0. So that means along x-axis, if this length is 1, it is going to start here, right? And you know that this cos t and sin t, right? X and y coordinates. So obviously you know that it is going to give you some kind of circular orbit. So like say, I mean, had t been fixed, so then say suppose say t were fixed, say z equal to say 3. So it would have represented a circle, I mean 3 units above z axis, right? 3 units above z axis. It would have been something like this. Okay, circle of radius 1. But now you see that at each time it is being elevated by t units. So that is why what is going to happen? It is going to elevate like this. Are you getting my point? It is going to elevate like this. Okay, because of the coordinate of j. Is it okay? Fine. So then, I mean, take any point here at time t, join it. So this is going to represent your vector r. So this rt is this, rt is this. Okay, fine. So this is the way I can define a curve in space. So for example, you see this I have already defined, and of course here t is called a parameter. T is called a parameter. Okay, so it is going to look like this. RT, I am going to explain it to you, and then this is the way you have sketched the curve whose vector equation is given by this I have already shown it to you. So now I'm going to ask you a question. Say you have to find a vector function that represents the curve of intersection of the cylinder x square y square equal to 1 and the plan y plus z equal to 2. So can you tell me how? So can you give me a parametric representation of this? Can you give me a parametric representation of this?
Ax is equal to cos t, y is equal to sin t, and z is equal to 2 minus sin t.
Yes. So basically, this vector x equal to cos t, y equal to sin t, and 2 minus sin t is going to give you the parameterization. Okay, and please remember, this parameterization is not unique. There can be more than one way to represent a vector. Okay, fine. So this is going to look something like what? Obviously, this is nothing but the cylinder. Cylinder, like something like that, which radius, I mean 1, and then this is a plane, this is a plane, so it is going to be something like this. So the plane is going to cut this, something like, it is going to cut it in a circle. Okay, it is going to be something like this. Okay, so you can get this, through this parameterization. Okay, so I'll just show you the figure here. So this is the figure you can see here, right? So this is what it is. So now let me come to the concept of derivative. Okay, derivative of a vector function. See, you definitely, I know that you all have done this, okay? But still, I want to quickly revise this stuff because later on we are going to deal only with this. Okay, derivative. Of a say vector function or vector Deluge function also it is called. Okay, so here we are going to do it in terms of one parameter. So now, say, suppose, okay, suppose I have a space curve like this, okay, and suppose at the okay, and suppose the parametric representation of this space curve, is simply given by RT equal to simply this xt, yt, and say j. Okay, fine. Say suppose this is R. Okay, and suppose at time t plus delta t, at t prime delta t, this moves from, let me just make it a bit longer. This moves from the position P to Q, right? So this is RT. So that means this is nothing but RT plus delta T. Okay. So that means this vector this vector, it must be what?
R del.
Yeah, so R T. Is it okay? Fine. So far so good, right? Okay. So now, of course, this is X, this is Y, this is J. Fine. So now let me consider this ratio. Let me consider this ratio. R T plus delta T minus R T divided by delta T. Remember, delta T is very small. Delta T, remember, delta T is very small. Delta T tends to 0. So then what is going to happen? What is going to happen? See, the vector RT plus delta T minus RT is given by this PQ, isn't it? So then if you multiply the vector PQ by an amount 1 by delta T, right? So you are likely to get a vector what? Which will be along the same direction, right, of PQ, but the length of the vector is likely to be more than PQ or less than PQ. Yes, go on. Delta T is very, very small. So 1 by delta C should be very, very big. You are getting my point? Right? Isn't it?
Yes, sir.
So that means
Yes,
you are likely to get a vector of length which is more than PQ, right? So if this is this, so then I mean you should get something like this. You should get this whole vector as R. Say I am doing all this stuff, although it is kind of repetition, but you guys are going to act as tutors later on, and definitely most of you are going to take teaching as your profession later on. Fine. So now what is happening? If you look at this vector, it has gone beyond the point Q, right? So this is going to act as a secant, right, to this curve. Okay. So now what is going to happen at this when Q is going to approach P, right? When Q is going to approach P, then as delta T tends to 0, what is going to happen? Then this vector as limit delta T tends to 0, this vector is going to be a tangent to the curve. Say, let me call this curve as C at the point P. Is it okay? Is it okay? Right?
Yes.
So what we are going to do? Basically, P is fixed. I am going to move it like this. So eventually, this is going to be a tangent, right? See, it was like this. I am going to move it like this, near and near. So eventually, it is going to be a tangent. Okay. So that derivative. So that derivative of R with respect to T is denoted by this, and this is nothing but the definition. Right? And then what happens? Then R prime T is a tangent. Remember, not D tangent. A tangent to the curve at the point P. So if you want to find D tangent, then what? I would like to have a
For
unit tangent.
particular point.
Pardon? Yeah, see, like say specific one. So then the unit tangent, I mean, in some book they call it big T, in some book they call it T cap, because cap generally it is used for unit vectors. Okay, so you know that I can get it simply by dividing it by its magnitude, dividing by its magnitude. Okay, now here there is a condition part. There is a condition part for the tangent to exist at a particular point, say t equal to t naught, at t equal to t naught, I would expect the derivative to be non-vanishing there. Derivative to be non-vanishing there. Remember that has to be there, because if it is a zero vector, I mean it is not going to define any tangent there. Zero vector, yeah, okay, let me ask you the question. I mean, zero vector is still a vector, right? Yes or no?
Yes, sir.
Right? Okay, fine. Now, why, I mean, in order to define a tangent, I still want the derivative to be non-vanishing at that particular point. Why, I mean, we are not wanting to have a zero vector as tangent? Can you tell me? Zero vector would prevent me from getting what?
But at that point, we do not have a direction, sir.
Exactly. If it is a zero vector, it will prevent us from getting a direction. If there is no direction, where do you get it? The tangent, isn't it? Right? Now is it clear the physical meaning of why, I mean, r prime t naught should not be equal to 0 where you are going to define a tangent, right? I hope it is clear now. Okay, so now, I mean, let me again summarize it. I'm going to show you much better picture now. Okay, so this is the definition of derivative. So it is simply for a vector function. It is similar to what you defined as real valued function. Say here, see this h I was defining as delta t. Don't worry about it. Okay, and of course the limit has to exist. Basically, limit has to exist means it has to exist finitely. Okay, so this is the way I defined it. You can see that this was PQ, and now because delta t or h is small, so like say this vector is likely to be of length more than PQ. So now eventually when Q approaches P, it becomes the tangent vector. It becomes the tangent vector. Okay, and then I mean all this whatever I have told you, that again here this is very important. Okay, r prime t is called the tangent vector to the curve defined by r at the point P, again provided firstly the derivative has to exist and the derivative has to be non-zero. Okay, so the tangent line to C at P is defined to be the line through P parallel to the tangent vector r prime t. Okay, so we will also have occasion to consider unit tangent vector, as I have told you. Some, I mean, some would they use capital T, right? And this is the unit tangent vector. Okay, fine. So let me see what this is about. Okay, so now let us come to surfaces and integral curves. Okay, the integral curve part I will come a bit later on, but surface I have already told you about surface, right? Yes. Surface, I mean, I can define it to be graph of a function of two variables, isn't it? Right? Agree or disagree?
Yes, sir.
Right? Okay.
Yes.
So basically, what I'm going to deal with now, surfaces and their normals. And then I mean, once you see the formal definition, you will see that definition I have taken from the NPTEL notes. So it is defining as what a function having 2 degrees of freedom. So basically, it's a function of two independent variables. That is what they do. So now, whenever we are going to consider surface, there is always going to be the notion of normal. Notion of normal to the surface at a particular point. Normal to the surface at a particular point. Can you tell me why this normal is so important? If I tell you that this normal is going to define a surface, would you agree? It is going to define a surface. Would you agree or disagree? And if you agree, why you agree? Yes? Can someone tell me? Okay, see,
I think
yes, somebody wants to say something. Yes.
From this normal vector, we shall get some tangent plane to this surface.
Okay.
So from this collection of our tangent space, we shall get some concept of surface.
Yeah, that is one way. That is one way of visualizing. The other way of visualizing is that, say, suppose I know certain points, right? Suppose I know certain points, right? At all those points, say, suppose I know this particular point lying on the surface, say, and then the normal is like this, and then another, the normal is like this. So suppose in a very small region, I know the direction of all the normals, right? So then what it is going to do, it is going to give me direction of those normals is going to give me the orientation of the surface. It is going to show me how the surface is shaping up. Is it okay? Right? So that is why you will see that in all the discussions of some surface, we are always going to have the normal associated with it. Fine? That is why this normal is very, very important to them. Okay. Now, I am not going to go into details, but I'd like to bring it to your attention. Like, you know that I can define a surface like the graph of a function. Okay, fine. So what happens? What happens in that case? I mean, this again, I can write it as this, and I may call this as a function of three variables. So this is like f of x, y, z equal to 0, f of x, y, z equal to 0. Fine. So far, so good, right? Yes. So now, can you tell me what is the difference between the way I have defined the surface through this function and through this one? Can you tell me what is the difference between these two?
Explicit, implicit.
Explicit, implicit. Okay, fine. Yes, one is done. Okay. This is explicit and this is implicit. Okay. So there are two ways of describing it. Another thing, yes. Explicit, implicit is fine. So can you add something more to that? Yes? See, one thing. I'm giving you a
Second one is level set of the function.
Exactly. See, what is happening here? Here, this is explicitly a function of two variables, isn't it? This is a function of two variables, okay? This is a function of three variables. This is a function of three variables. See, remember, suppose I consider a function of two variables, then what is going to happen? What is going to happen? The graph of the function, suppose z equal to f of xy, graph of the function, it is going to be a surface, right? It is going to be a surface, right? And surface is the based, I shouldn't use the word based. Like say, you can visualize a three-dimensional object at most up to a surface, or not three-dimensional, that you can visualize the graph of a function only up to a surface, isn't it? So only the graph of a function of two variables is visible, right? It can be visualized. Okay. So now here, what is happening? If you now cut this surface with some planes parallel to j plane, then what is going to happen? This plane and the surface, they are going to cut at some curves, isn't it? Is it okay?
Yes, sir.
Fine. They are going to cut here. Say, suppose I have another plane here, so I may get some curve like this. Okay. See, my function was j equal to f of xy. Suppose like this height, suppose this is say c1. Suppose this height, say this is c2, the value of j, right? So then in the first case, it is going to give me f of xy equal to c1, and in the second case, it is going to give me f of xy equal to c2, right? And obviously, under if you follow implicit function theorem, which I'll come to that later on, right? Under certain circumstances, from both of these, you can express y explicitly as a function of x, isn't it? And they are going to define some what curve in the xy plane. Is it okay with everybody? Right? Isn't it?
Okay,
Yes.
sir.
Yes,
Right? And these curves are called your level curves. Okay. In fact, in sample, what they are going to do, they are going to simply take the projection of these curves on the xy plane. For example, projection of this is this one, projection of this will be this one. They also define them as level curves, but there are other names for that. They are also called contours or contour curves. They are also called contours. These, and this is level curve. Okay, this is level curve. Okay, now this is fine. So what we get from a three-dimensional surface, if you take the level, what should I say? Three-dimensional surface, you get level curves, right? And the three-dimensional surface you are getting from a function of two variables, right? Now, if I take a function of three variables, say f of xyj, can you visualize it? Because I've been needing some kind of four-dimensional space, isn't it? Right? I've been needing something like that. Okay? Fine? But if you consider the and that is why since we cannot visualize them for functions of three or more variables, the surface generated by them, although we cannot visualize it, they are called hypersurfaces. Okay, so now if you take this approach, simply by plugging in the value of, say, suppose this new variable is something like new, say, okay. So if by plugging in new equal to, constant, like this, what I should get? Are you getting my point? A function of two variables have given me a curve through this approach. If I going to adopt the same approach for a function of three variables, it is going to give me what?
Level
Surface.
It is going to give me level surface. It is going to give me level surface. Okay, it is going to give me level surface. Okay, so that means what the question that I was asking you is that through this approach, I can get the level surfaces. I can get the level surfaces of this function, capital F of x, y, z equal to 0. Okay, so let me do a quick recap. After that, I'll go back to that normal. I'll go back to that normal, I think. This one I'll talk about in normal later on. Okay, this is the definition of level surface. See, the set of all points in the three-dimensional space. Not all points, so they are taking a subset of R3. They are calling it omega, right? And in such a way that f of x, y, z equal to c, for some appropriate value of the constant c, is a surface in that omega. Okay, and this surface is called a level surface of F. I'll show you a picture of that. And again, what is the assumption? What is the assumption here? Is that the gradient is non-vanishing. The gradient of that function, because from this function you can get a gradient vector, right? So this assumption is that the gradient vector is non-vanishing. I'll come back to that gradient vector again because we will have to deal with that all the time. Okay, fine. So now let me show you this level curve. So for example, say this is a two-dimensional the function of two variables, and the graph was a surface. Now if you intersect this surface with some j equal to constant, right? So it is going to lead you to something like f of x, y, z equal to what? Here, sorry, f of x, y equal to k. So it is going to give you a curve. So these are nothing but level curve. These are nothing but level curve. Okay. So this is about level curve. So now in the next slide, you are going to see some surfaces, and like some level curves, some level curves. So can you map them? Which one is going to give you, what kind of level curve here? Are you getting my question? Say here I have got 6 surfaces, and here I have got 6 figures of level curves. So you have to map those surfaces to this level curves. Can you give me 1 or 2 answers here? Yes, this is the easiest. This one, E is the easiest. Can you tell me? E will be mapped to what?
3.
E will be mapped to 3. Right? Similarly, this is also easy. This is also easy. D. Say there is one like peak, and this is peaked. This one, D will be D will be with 5. See, there is one peak, there is one peaked here. Is it okay?
Yes, sir.
Fine. So similarly, I mean, you can find the others also. At home, you can try. So now let me come to functions of 3 or more variables. And as I have told you, like say, if you take the function f of x, y, z equal to x squared plus y squared plus z squared, you cannot, I mean, plot it, right? But if you assign some constant value to that, it represents the equation of a sphere, right? So then, say for different values of that constant, you get spheres of different radii like this. Is it okay? Fine. So this is the concept of level surface. This is the concept of level surface. Okay. So what I'm going to do, I'm going to now. Okay. Fine. So now, because you already have an idea of level curve, level surface, so now let me get back to that gradient. Okay, fine. See, suppose this is a surface in, say, 3D space. Okay, fine. And I may consider this surface belonging to some omega, which is a subset of R3, right? So then suppose this one is f of x, y, j equal to k, say. Okay, fine. So then you know that at any point, say x naught, y naught, j naught, x naught, y naught, j naught, what happens? Like a normal is defined by the gradient vector of the function f at the point x naught, y naught, j naught. Is it okay with everybody? Fine? Okay?
Yes, sir.
Right? So what we are going to do, we'll try to, I mean, derive the equation of a tangent, equation of a plane in 3D space, and then equation of a tangent plane to a surface later on. And I'll be pretty quick, don't worry about it. But see, again, I am doing, many of the things from scratch so that even if some of the concepts were not clear to you, it becomes clear to you now. Okay. Say, suppose I am considering a plane in, say, 3D space. Plane in 3D space. Suppose my situation is something like this: x, y, z. Okay. Now let us consider a fixed point here. Let us consider a fixed point here. Say, suppose this is P naught, right, on that particular plane, and suppose the vector associated with that fixed point, so this is a constant vector, R0. Okay, fine. Always remember, whenever you want to develop the equation of some geometric shape, what you do in that particular geometric shape, you consider a fixed point and then you consider a variable point. Okay, eventually the equation of that particular shape is going to come in terms of the variable point. Remember that. Okay. So now let us consider a variable point here. So let me call it say P xyz, P xyz. Okay. So then as suppose here. So then I'm going to call this vector as R1. Okay. Then obviously your this distance again see. Let me tell you, depending upon whether you take these words to the right or left. So now this distance is going to be your, the way I have drawn it, this distance is going to be this, isn't it? Is it okay? Is it okay?
Yes, sir.
Fine. Had I taken this point on the right of this P naught, then it would have been R minus R naught, isn't it? Right? Now let us consider a normal to be planned at the point, say P naught. Okay, so then obviously this normal is perpendicular to the vector like say P naught, right? Is it okay with everybody?
Yes, sir.
Right? So this means n cap dot P naught is nothing but R naught minus R. So this is 0. So I can write this as simply R minus R naught dot n cap. This is equal to 0. So this is nothing but the vector equation of a tangent plane. Okay? Right? Tangent plane passing through the fixed point, you're given by the vector R naught. That's it. So I mean, if you know the components of this vector n, so obviously you'll be able to find out the equation of the tangent plane. Say in case your n was simply say nx, ny, and z. So then if your I have already written P is xyz, P naught is x naught, y naught, z naught. So this would give you what? Your nx, x minus x naught, plus ny, y minus y naught, plus nz, z minus z naught. This is equal to 0. Is it okay? Fine. Now, if I use the same concept, in order to determine the equation of a tangent plane, to a surface which is given as a level surface at the point x naught, y naught, z naught. Then what is going to happen? I know that. See, the same concept I have used. Like say this I have called R naught. Say like say let me take a neighboring point here. This point say now let me take it towards right. This is R. So this is P. This is P naught. So if you use the same approach here, right? Only thing is that instead of n cap, now what I am going to do, I am simply going to use R minus R naught instead of n cap. I am going to use grade f at the point x naught, y naught, z naught. This is equal to 0. Is it okay? Is it okay with everybody? Right? So that is why this is going to eventually get you fx x naught, y naught, z naught, x minus x naught plus fy x naught, y naught, z naught, y minus y naught, and again plus fz z minus z naught. This is equal to 0. As easy as that. Okay, so I guess I'm going to stop here today. like say today, I am having kind of a cartel class. So in my next class, what I'm that integral curves and surface, we're going to deal with that. And again, there are many things. That I would like to discuss about, particularly the orientation of this normal. I mean, how it is going to look like if it's oriented like this, or it is oriented like this. Because I have seen that the students they get confused a lot with that. So I'll describe them also. Okay, and the derivative of this stuff, all those concepts I have taken from Stewart's calculus book. Stewart's calculus book. So I mean, you can freely download it from internet. So there are many versions in internet. You can find it. Okay. So if you don't find it, I can give you a link. I have that copy. Okay. So then I'll see you when? Not tomorrow. Yes.